Okay, here we go. Somewhere in the homework, there was a factoring cubes problem. I don't remember where it was, but we need to make sure we know how to factor cubes. You did this last year. It's called the difference of cubes. You recognize these are cubes. So the factorization for the difference of cubes, do you remember, is a smaller parentheses and then a bigger parentheses. There's a factorization for this, just like there's a factorization for this. This is called the difference of squares, and every single time it's factored the same way. There's a pattern for it. Same thing with cubes. When we factor cubes, anybody remember what goes here first in the little parentheses?
2 minus
3y.
Yep, 2 minus 3y, that's exactly right. I want you to look at it. Where did the 2 come from? The cube root of 8. Where did the 3y come from? Cube root of this. Right. Minus, minus, they match. Now, the second parentheses, you square that number. You square that number. And you multiply them together. This sign is always the opposite of this one, so it's going to be a plus. Now, why is this one a minus? Because the problem is a minus. This is always the opposite, this is always plus. So there's your factorization, we're done. So if we had a different problem, 64x cubed minus 27, or let's do plus, 64x cubed plus 27. What would go in the first parentheses? These are cubes now, so what would go in the first parentheses? 4x plus 3. And then we square this, square that, and multiply them together. Now that's a plus, because that's a plus. So what's this? Minus, and that is a plus. All right, you need to know how to factor cubes. Number 2, you actually had to do. Those of you that thought that was linear, I need you to go back and look at those points again. They were not in a straight line. There was definitely a curve there. And the equation, I don't know, I'm looking at Blake's paper, I think that's the right equation. That's the regression that came out when you did the quadratic regression on that. And then it said if you work on that for 8 minutes, so you just plug in 8 here. And that gives you the answer to that. Anybody have a question about number 2? Okay, number 3. You graph this, and let's get our calculators out because we want to do the rest of the problem now. So you graphed that. So let's put that equation into our calculator. Okay, so let's put that into our calculator. Just use a standard window. And you have already found the 0. And I can't remember for sure, but I think everybody may have gotten that right, actually. Now, when I graphed it using a standard window, I got a picture that looked like this. Is that kind of what yours looks like? Now, for the next part of the problem, that really isn't totally good enough. this right here would be a relative or a local maximum. Would you agree with me? And that I can see and that I can find. So let's go ahead and find that point right there. The directions say find the relative local maximum. We're going to find it right there. It is. So I will do second calc. And normally when I'm looking for the zero, I just click down to zero, right? Where do you think I'm going to go this time? Down the maximum. Yep. And then I'm going to set my left bound somewhere over here. My right bound on the other side, and then put it about at the top of the hill. And my maximum is negative 0.76, comma negative 0.544. What do you think? Is that about what yours says?
Yeah.
Okay. Now, what about the minimum? What am I going to have to do about the minimum?
Make the window bigger.
I'm going to make my window bigger, and specifically, I'm going to have to make my Y min bigger. I gotta go down farther. I can't see that bottom point. So I'm going to adjust my window, my Y min. I'm going to send it down to about, oh, let's try negative 30.
Oh gosh, that's 17 will work.
Oh, yeah. Well, negative 30 works fine, but that was bigger than I needed. But now I can see my minimum. So guess what I do? Second calc, go down to minimum, set your bounds on either side. Now remember, this is the point you're looking for. So left bound's over here, right bound's over here. And my minimum is 0.76, comma negative 12.56. Are you okay with that? So finding the max and min from the graph is exactly the same as finding the zeros. Okay? All right, next you had to find the domain, and a lot of you have written on your paper, not necessary, because when you looked at problem A, you said, exactly correctly, you said x can't be 1. Absolutely not. Graphically, that would be a vertical asymptote. And then you said, whatever's under the radical has to be bigger than or equal to 0, so x has to be bigger than or equal to 2. So this is what you said. And I put a circle around this and said not necessary. Can you explain to me why that's not necessary? I didn't mark it wrong, but why is it not necessary? Bailey?
Because that x is greater than 2.
Yeah, if you tell me x has to be bigger than 2, then I don't need to worry about that, right? That's why I wrote not necessary there. And remember, I always grade my papers on the elliptical, so my handwriting is a disaster. B. Domain for B is all real numbers. I don't know why some of you said other things. What causes issues with domain? Denominators and radicals. Do I have even one? No, your domain is all real numbers. All right, now we need to look at number 5. You already found, hopefully, the horizontal asymptote. And you found the horizontal asymptote by doing what?
Looking at the colors.
I hope just looking right there. That's all you needed to do. Let's review those rules again for horizontal asymptotes. If the powers match, then that ratio is your horizontal asymptote, period. What if the power on top is bigger? If the power on top is bigger, then no horizontal asymptote. What if the power on the bottom is bigger? The asymptote's at 0. Okay? Now, horizontal asymptotes are equations. So you can't just write the number 2. You have to write an equation. This is the equation where y equals 2. Okay? All right, now let's look at this problem. We got a feeling there's a whole bunch of other stuff here. When you look at that problem, you've got your horizontal asymptote taken care of, okay. When you look at this problem, do you think about factoring it maybe? It looks like it factors, so let's go ahead and do some factoring and see what happens. Alright, so I've got it factored completely. I think I took a 2 out of the top first, and then I factored. What do you think? Is that okay? Now, what do you notice right away? What do you notice?
X minus
These guys will cancel, right? And the problem reduces to just this. Now, the fact that problem reduces is huge. That means you have a hole, a removable discontinuity, at x equals 4. Okay, remember, denominators cause us problems. Why do denominators cause us problems? Because they can't be 0, right? So we have 2 problems here. The good news is we can cancel that one out, so now we really only have one big problem, where x equals 2. I have a I erased my picture. I have a vertical asymptote at x equals 2. And why do I have a vertical asymptote at x equals 2? Denominator can't be 0, right? The other issue canceled out. It removed. How do I illustrate that graphically? Well, keep in mind, in the original problem, could I put 4 in? No. So I have to reflect that in my picture. So there's going to be an opening in the picture, an open circle, not an asymptote, just an opening at the point where x equals 4. Well, where do I put that point? What would the y coordinate be? Well, come back to your problem. What do you get if you put 4 in? 10, 5? So you have a hole in your picture at 4, 5. I'm going to go ahead and erase the original problem. So I have a hole in my picture at the point 4, 5. Now, where did the 4 come from? It's what canceled, right? The only way you can get holes is if you can remove them. And the only way you can remove them is by canceling. Most problems aren't going to have holes because most of the time you're not going to be able to cancel. But if you can cancel, you will have an opening in your graph. And the x-coordinate comes directly from the factor that you canceled. Now, where did the y-coordinate come from? Plugged it back in. And where did I plug it back in? Not to the original problem because it's not going to work in the original problem. You have to plug it into your reduced problem. Vincent?
If you had x plus 4 and x plus 4, would it be negative 4?
It would be, yes. It's whatever makes the factor 0 that you cancel out.
Okay.
Yeah.
So the vertical asymptote's x equals 2.
Yes, because x cannot be 2. That's called a non-removable discontinuity. That one you're stuck with, and that's going to be an asymptote. That's going to be an extra break in the picture. So I have a hole at 4, 5. I have a vertical asymptote at x equals 2, because my denominator can't be 0. Now, what do we mean by x-intercept and y-intercept? What are we talking about there?
Those are the coordinates.
Those are ordered pairs, points. What points? Points out here?
On the graph.
On the axes themselves, right? Tell me what you know about any point on the x-axis. Y equals 0. So I'm going to come back to my equation. Here's my equation. And I'm going to let y equal 0. Do it up here. So if I let y equal 0, this is where I am. Now how do I solve that? Let's multiply this over to here and it just stays 0. Right? You multiply both sides by x minus 2. So what does x have to equal then?
X equal 1.
Negative 1?
Variable.
So my x-intercept is the point where x equals negative 1. Now, what do you know about any point on the y-axis?
X is 0.
X is 0, so let's put zeros in for the x's. And what do we get there? Ooh, negative 1 again. Did I do my arithmetic right? And there we are. All the information's filled in. Now, given what we've got here, I'm going to go ahead and sketch in the graph, connecting the dots. Which of your BFFs is this a version of? Reciprocal function, and that makes sense, doesn't it? Because it has a numerator and a denominator.
This one's absolute.
Maybe tomorrow we'll do another one of these. We have a couple other things we need to talk about. Number 6. Is the function drawn below bounded? Now, I wasn't as picky on this question as I might have been. I really looked for the word in your explanation, bounded below. The actual answer to the question is no, it isn't bounded. Because to be bounded, you have to be bounded above and below. So the best answer to this question would have been no, but you are bounded below. Some of you said yes, because you're bounded below. And really that's not the right answer. But I gave you credit for it because you said the word bounded below, which is what it is. Bounded means above and below. So think of your sine function. That is bounded, for example, right? What function is this, number 6? Now we can talk about it. What is number 6? That's your absolute value function. Very, very good. Okay. Today, first of all, some of you look like you're sound asleep. I don't understand that you've had 3 days to rest. You should be full of vim and vigor. We have one thing to talk about today, but before we do, I was going to give a quiz, but I don't have time, so we're just going to do this orally. We're going to see if we can name all of our BFFs. Name them today. Can we name
Yes.
them? You can name them all, Dan?
Oh, no.
Okay.
Like
All right,
three.
let's have you give us one.
Absolute value.
Absolute value. I'll keep track of them here so we know we got the absolute value. All right, somebody give us another one. Dan?
Logarithmic.
The logarithmic function, the log function, ln function. Yeah, Victoria? Sine function, S-I-N-E. Yep, perfect. Got one. Yes, Alexis? The cubing function, absolutely. And that one has kind of that, the picture we graphed a minute ago where we were doing maxes and mins on that, that was a cubing function. Yes, Jasmine? Cosine. Remember, how are we going to keep sine and cosine separate? Sine goes through the origin. Jamie?
Exponential.
The exponential function, perfect, nicely done. Audrey?
Linear function.
Linear, yeah, the basic one of all, the linear function. John? Squaring function, which is your quadratic function, yep.
Reciprocal
The
function.
reciprocal function, which is a variation we have right here. Good, we're on a roll. We got 3 more to go. Mahela?
The greatest integer.
Greatest integer function, yep, there's another one. Rachel?
Identity.
Well, the identity and the linear are the same. I call it linear because it's a line. Your book calls it identity. So yeah, those are the same thing. Either description is absolutely fine. Jamie?
Square root.
The square root function.
Logistic.
Very good. Did you look that up or did you remember
I
it?
looked it up.
Thanks for being honest. The logistic function. Now, what you need to be able to do, this is awesome, we have them listed. Could you give me the shape? How many of these could you give me the shape for right now? Half of them? Let's work on being able to give me the shape for all of those. So if I said, what does a cubing function look like? You would say, it looks like this. What does the reciprocal function look like? It looks like this. Get to where you know those shapes. It's going to come in handy today. Because today what we're going to do is graph what are called some piecewise functions. Okay? Some piecewise functions. So I'm going to erase all this other stuff. And we're going to do that right now.
I used to be so bad last year.
Now, sometimes we look at this and we get scared. You two need to sit up. Okay. You know, did you mix coffee? Bring in coffee or something. I don't need no way. I know something's good. All right, here we go. We're going to graph this thing in pieces. We are not going to be afraid of it. We are not going to be afraid of it. Now, there are a couple of different strategies that we can use. If you're working like you should be with a pencil and an eraser, one strategy you can use is this. Forget everything and graph the absolute value function. The absolute value function looks like this, right? I don't need to plot any points. I don't need to do anything because it's one of my BFFs and I remember what it looks like. Now that is the entire thing. This particular picture is broken where x equals 3. So don't draw this in, but just think of a line right here where x equals 3. Think of creasing your paper, and that's where the picture is split. What part of the absolute value function am I interested in? The part to the left of the fold or the part to the right of the fold? If I think of folding my paper here, creasing my paper, where x is 3, which part of the absolute value function am I interested in? The part to the left. It says x is less than 3. Isn't that over here? So I'm simply going to erase this part of the picture. It's not important. The only part of the absolute value picture I want is the part that's to the left of the 3.
Do we still need an arrow there?
Here?
Never mind.
No, it stops right here. You need an arrow over here though because you're going forever and ever and ever. Now, I'm going to forget everything and I'm just going to graph y equals negative x, which by the way is this line right here. This is the line y equals negative x. Now how do I know that? Well, it's the negative of the identity function. So instead of going like this, it goes like this because it's been turned over. Now what part of that line do I want? I only want the right part, so I want from here down. The rest of it I erase. Now be careful, don't get carried away. It overlaps the greatest, or the absolute value function. So just erase the part of it we don't need, and there it is. You're done. It's that simple. Start at the bottom this time. What's this? A quadrant. That's your little quadratic, right? I want to make sure I have it the right shape. I want to make sure I'm not making it too fat. Oh, that's about the worst parabola ever. Okay. So there's my whole parabola. This time, the picture is broken here, where x is 2. You in agreement? Which part of the parabola do you want? It says x is less than 2, so which part do we want? We want everything to the left. We do not want this part. So it's going to start right there. At the point where x is 2 and y is 4. That's the point where it's going to start. Why is that an open dot this time? I put a closed one over here. Because it's not included, right? That point's not included in the parabola. Right, now what shape is this? That's just a line. So let's see. I'm just plotting a few points to make sure I get my shape right. In which part of that line am I interested in, Grace?
I just had a question. Where'd you get the 4? To like know that that's what
Here?
it's on.
Okay, remember, if x is 2, this is the curve, x squared, squaring function, 2 squared, 4. Yeah, looking for the y values. Now that's the whole line. Which part of that line do I want?
Greater than 2.
Yep, so I got another open circle down here. I'm going to erase this line. Don't need it. There's the crease of the paper. It's not really part of the picture. I'm just pretending I folded my paper there. And what in the world is this?
It's just a vertical line.
Well, the whole thing would be a vertical line, but in terms of the problem, it says if x equals 2, y equals 3.
So it's 2.2.
2.3. Or 2.3. 2 comma 3. This says, remember, this is y. So it says y equals 3 if x equals 2. If you just look at that piece of it, it says y equals 3 if x equals 2. That just is an ordered pair. That's just a point. 2 comma 3. If you graph the whole thing, it would be a line, but we only want it where x is 2. So it's just that one particular little point. Is that a function? Absolutely it is. Is it a continuous function? No way. What is its domain? All reals, perfect. It says right here. Here's the x's. Equal to 2, greater than 2, less than 2. Isn't that everything? What's its range? not all reals. The range, certainly you have y's greater than or equal to 0. Would you agree with that? But you also have y's where? Less than -4. That came from this equation, so that's the 0.2 comma -4. So less than -4. All right, let's have you try one with your partner. Let's try that one. See if you can graph that. Keep in mind where your break is this time, where your fold is in your picture.
Like this is like y equals, so it's like y equals x. And like, yeah. And then, yeah, so you know that x, so your paper is going to be like x is greater than or equal to, like, it's like 2x.
What do you think? Are you getting something that looks sort of like this?
Yeah.
So let's talk about domain and range again. What's your domain? All real numbers right here. It tells you that's your domain. That's everything. What about your range?
Y is greater than.
Y is greater than -2,
Less than or
or
equal to
Y is less than or equal to
-4.
-4. There you go. There you go.
Can you
Emma,
remember how you got the second one? The 2x?
how we graph that? I plotted points. So if I let x be 1, I get -1, or yeah, if I let x be -1, I get -2. If I, that's clear down here, I erased that part of it.
Okay.
That this was the line, but I erased this part of it because I had to be less than -2. But if I put in -2, I get -4. If I put in -3, I get -6, and so on. Yeah. Yeah. When in doubt, plot points if you're graphing. All right, speaking of doubt, who had an issue with a homework problem? Did anybody have something you were worried about in the homework? Hannah,
42.
the 3 functions with infinitely many local extrema. Now, what do we mean by local extrema? Relative local maxims and mins, okay? So for example, if I draw an absolute value, it has 1 local minimum or relative minimum. It also has one absolute minimum, that happens to be the absolute minimum. So that isn't one of these. You need to think of a picture that has lots of low points or high points. Certainly the sine curve is one, because when you graph a sine curve, wouldn't this be a local a maximum and a local minimum, local maximum, local minimum, and so on? So there are infinitely many in the sine, and of course, if that's true of the sine, it's true of the cosine. All right. Now, can you think of another one of all your other curves? Which other one has high points? The linear function has no relative maxes and mins because it doesn't have any like tops and bottoms. It just keeps going forever and ever and ever. Kayla? The cubing function likewise. Now, if the basic cubing function looks like this. But if you alter it, put some other terms in it, it will have this shape. It will have at the most one maximum and one minimum. It is the greatest integer function. Because if you look at any particular interval, isn't the relative maximum different for each particular interval? If you look at this interval, that's the highest the points go. It's also the lowest they go. But if you look at this interval now, this interval has a different high point and low point. This one has yet a different one, and so on. So it is your sine, cosine, and your greatest integer that have infinitely many high points and low points. That's different than saying infinitely tall. This goes on to infinity. This has no maximum at all. All right, good. Anybody else have a question about one of those problems? Amelie? 28. The two functions whose graphs are identical except for a horizontal shift. Yep, sine and cosine. Same curve, shifted sideways.
What is this?
Yeah. Yep, they're just shifted pi over 2 units, half pi horizontally. Anything else from the homework? 21. Three functions that are decreasing on the interval from negative infinity to 0. So in other words, drawing them left to right in this space right here, negative infinity to 0, drawing them left to right, your pencil is going down.
So like 5.
What?
Number 5, you want the linear function?
Linear function.
Well, it's going the other way.
Yeah, the linear function is actually increasing on that interval. I need something that's going the other direction. So I can think of one right off the bat. Absolute value. Jasmine, do you see what I mean? Going this way, it's decreasing. Okay, so that's one. What's the shape that's very close to this one? The squaring, the quadratic. That one's decreasing. The reciprocal function, let's see, we're talking about this interval, it is decreasing. Yep, it sure is. Going down left to right, that's exactly right. How many are we supposed to be finding? Oh, we got them all, there they are. So basically, Jasmine, on the left side of the picture, you want it going down. So this would not be one because that pencil's going out on the left side of the picture. Anybody else? 25. The four functions that do not have end behavior. Oh, that notation might have bothered you a little bit.
It's just saying that the ones that don't go up.
That's just saying that as you go to positive infinity, so in terms of the picture, as we go this way, as x goes to positive infinity, was that also positive infinity? Yeah. So remember, f of x is y. So they're telling us x is going to positive infinity. That means we're going right. Now you want y going also to positive infinity, so that means up. So as you go right, your pencil is going up into space. So that linear function that we talked about a minute ago, that would be an example of one. As you go right, you're going up. Another one would be the absolute value function. As you're going right, you're going up. Another one would be the quadratic function. As you're going right, you're going up. How many are there supposed to be?
This is 4 functions.
4. Okay, so we've got 3 of them right off the
Oh, it
bat.
says that do not.
What?
It says that don't, do not.
Oh, that do not. Oh, okay, sorry. Okay, well, these are not.
Yeah.
These all do. So now we need some that don't. Sorry about that. How about the reciprocal function? As we go right, as x goes right, what's happening to your y values? They're coming down, so that's one of them. How about your logistic function? As you go right, your pencil actually is going up, but not to positive infinity. It's got a ceiling, doesn't it? So that's heading toward 1. The reciprocal function's going to 0, the logistics going to 1. Let's see. How about, that's the name of that. Let's see, what else have we got? Sine and cosine, they are not approaching infinity. They're bouncing back and forth between 1 and -1. So we only needed 4 of them?
Yeah.
That's the 4.
Thank you.
You're welcome. Okay. All right, so tonight practice a little bit more with the DFFs. And